good afternoon. I'm Kevin McIver. I'm here today to talk to you about HPC performance and why bare metal is still the king. When we look at physical compute clusters are really just a set of nodes, right? These set of nodes can be turned into either a high-performance computing cluster with traditional InfiniBand or Slingshot interconnects. It could be an OpenStack cloud with high-speed Ethernet, or you could run it as a Kubernetes cluster, which could actually rely on either. You could do high-speed Ethernet, you could do low-speed Ethernet. When you look at resource allocation in these environments, Slurm relies on the concept of doing an exclusive contiguous allocation for hardware. So you take a physical set of compute resources and allocate them to a single user. The single user means that they have no noisy neighbors. They don't have any limitations in terms of access to hardware topology, information about resources available on the compute node, everything belongs to them. When you look at OpenStack relies on the concept of using VMs. So these VMs are going to be sliced to some sort of quality of service, which is going to guarantee you access to a certain amount of vCPUs, certain amount of RAM, and sometimes network bandwidth along other things. You also are usually going to get broken up along a NUMA domain boundary. So you're going to have good performance within your little slice. And if you need more resources, you can just get more resources. When you look at how Kubernetes scales, it's actually pretty nonsensical, because what they're going to do in Kubernetes is just allocate and scale out vCPU and RAM with no real quality of service requirements around access to network resources or other shared things. You have no quality of service guarantees in terms of access to anything other than really RAM and vCPU. Some pods may require access to resources that need additional plugins to be managed by Kubernetes. When we talk about NUMA domains, it's really what the core underlying resource that's being provisioned is. And so this is a look at a single block diagram for an AMD 9554 EPYC Genoa series compute node with 2 compute CPUs and all the associated RAM with some GPUs attached. The GPUs are going to be attached physically to one compute socket. To get to the other CPUs, you actually have to traverse a socket-to-socket interconnect. That adds a bandwidth penalty and a latency penalty for any access by CPUs to GPUs located on the other CPU. Unequal access to these resources means that if you're actually caring about how your application scales, you need to know which CPU you're on. You need to know the types of information about your hardware topology. Otherwise, you're going to get inaccurate assessments, right? So your real performance access to network, if you're trying to scale out, also matters, because the CPU that has access to the GPUs may not actually be the one that's connected to the network fabric, right? And this happens a lot. So when you look at these different resources, you really care. And so to scale your job in Slurm, all you have to do is add compute nodes, right? You say, I want 1 node, I want 2, I want 3. You get everything. When you're scaling in OpenStack, you're just going to change shapes. So you're going to go from something that may be a 16th to something that's a quarter to something that's a half to something that's a whole VM size on a physical compute node, right? That's going to come with associated bumps in vCPU, RAM, and network bandwidth. When you look at Kubernetes, say you're scaling this application that's pod A, this pod A application may perform quite differently in these different instances, right? Each application's throughput is not going to be consistent. So if you're trying to do something in parallel, you're actually going to end up with wildly different answers going from a smaller pod to a bigger pod, or a pod that's in a different physical location, or one that may have workload interference coming from other pods, because this pod may be competing more for network bandwidth, or this pod may want GPUs, right? And so all of these unfair resource distributions mean that while it does work, your delivery has been simplified, you're not really sure what your software solution is doing. And so monolithic applications still have a place in core delivery in HPC. Abstracting away that hardware simplifies delivery, but it comes at a huge cost. And so when you're considering high-performance computing environments, it's rarely the right answer to say, let's shove Kubernetes in. We recommend using CIQ's Apptainer for anything to do with HPC applications. So there's also the hypervisor tax, which is a fun thing I like to mention. So when you look at Azure, what Azure is going to do is they're going to take a CPU off each of these chiplets. So they own a core that you can't use. And that, by definition, is going to restrict what you can do with your hardware, because they have to run their hypervisor stack. So these resource providers come at a tax. There's a hypervisor that has to add overhead, and it reduces the available resources compared to bare metal. So bare metal is still the king. So for maximum performance, we recommend you buy hardware. We use Ace Computers. We recommend you do too. They're a great team. They work with OEMs like Gigabyte. They work with Supermicro, and they get us what we need when we need it. So if you like the performance of bare metal but don't want to deal with the hassle of running a data center, we recommend Corvid HPC. That's who we're with. HPC as a service means that we can take our last gen AMD Milan offering and be 10% faster core for core versus AWS's latest and greatest AMD Genoa offering, right? This is a benchmark from a CFD application where we went and dug through a bunch of cases with a customer that helped drive basically a close there, where we were getting more performance per core per dollar. So bottom line, Corvid HPC, Ace Computers.